When we do strength testing, we do what we call a 1 repetition maximum. So we basically find out how much a person can lift at one time. So here we're set up to do a bench press. What's been done, because doing an actual 1 repetition maximum can take quite a while and may not be the completely safest way to do it, is that you could come up with developing an equation to estimate a 1 repetition maximum from like a 2 to 10 repetition maximum. So a potential lab idea is that you bring the students in and we do a setup where we max them out. We make sure that they can, what they lift, that they can do it more than once and they can do it less than 10 times. Then after they've rested enough, we would come back and they would do an actual 1 repetition maximum. And essentially we'd see, well, how well could we correlate, or how well could we predict the 1 repetition maximum from these 2 to 10 repetition maximums. So that's something that we do. Another add-on to that would be, obviously this has already been done, so there is an equation out there. So an additional thing would be to check just, well, how well did that equation do? How, because we have their actual 1 repetition maximum, how well did that equation do in terms of predicting what their actual 1 repetition maximum was?
And it's a linear equation? Or is it a curve?
It's a linear equation.
Okay, cool.
Yeah.
So,
What gets a little more complicated in developing an equation is that somebody might lift 3 times, and somebody else might lift 5 times, and somebody else might have lift 6 times, so that makes it a little more difficult in terms of establishing the equation. But checking out the equation, yeah, it's a simple linear equation.
So for a given student to estimate their 1 rep max, would you try and have 3 or 4 data points? Like, this is the max you can. For this week, you're able to do 5.
Really, each student would probably only have 1. I was thinking each one would just have 1 data point. They would have they did 4 repetitions, this amount of weight. And somebody else, when we got them, they did 6 and they did this amount of weight. I guess, yeah, if we were doing a real study, we would try to figure out how much they did twice and 3 times and 4 times. But we'd kill them off if we did it that way. So the idea here is that we could put somebody on a bicycle and we could have them ride. And so my idea was that they would probably ride at a power output of like 50 watts and 100 watts. And they would ride for 4 minutes at each one of those. And while they're riding, they would wear a heart rate monitor so we could measure their heart rate. And they would put on this contraction so we could measure how much oxygen they're using. So we're measuring the oxygen uptake is going to then tell us, in essence, how much energy they're producing. So from a kind of a mathematical standpoint, what we could then once again do is we could develop an equation to estimate their oxygen uptake from their power output. And so in this case, we'd have 2 data points. We would have 50 watts and 100 watts, and we'd have their VO2 at each one of those, and then we could develop an equation to estimate the VO2.
VO2 being the volumetric?
Being what we're measuring here, yes. And once again, this has been done, so there is an equation out there, so we could compare what they come up with, with what is actually out there. Now, there are other things that we can measure during this, but I'm not sure how to turn it into more than just an observation. So certainly we'll be measuring their heart rate, and so we'll get their heart rate and their blood pressure like at rest and at 50 watts and 100 watts, and we're going to see those things, we're going to see those things go up. but I wasn't really sure how to make that into more of a study, other than just, oh, this will be interesting for them to realize, okay, yeah, we can see the heart rates, the heart's beating faster, and so forth. But for kind of then the math part, this was the idea that I had.
Do you think, I mean, that relationship isn't linear because the heart doesn't continue increasing its rate forever? So.
Well, yes, correct. I mean, we do assume, well, yeah, and that varies a little bit from person to person, and there is an estimated maximal heart rate for everybody, but your heart rate, your maximal heart rate is mostly dependent upon on age, but there's still huge variations. I mean, certainly, I didn't think we wanted to max people out. Didn't think we wanted to make them do maximal. Plus, the other thing that the higher we make them go, the longer we make the test, limits the number of people that you can do. So you figure, I'm figuring that this will be, they're going to have to be on here for at least 8 minutes, and then we would fairly quickly get the next person going. And we can even if we wanted 3 data points without taking more time, we could use an assumed resting oxygen uptake on these individuals. So we would have a resting of 50 watts and 100 watts. So we'd have 3 data points with one of them that we just calculated, but we didn't actually measure, to maybe save a little bit of time. Because it's still going to take 12 to 15 minutes probably per student to be able to do the test.
So as you organize the logistics of your students, think about having them in groups of maybe 3, with one person actually getting on and everybody working on the data, something like that, or else, for a group of 20, it'll be a long time. You have every single student do the data.
And on this one, certainly, I will be here to run the metabolic card, so you guys aren't going to have to worry about, about that part. I think on the bench press one, and I'll probably still have somebody here, but you guys can learn how to do that. You can do the whole demonstration of that one. But this one, I'll be here to run the metabolic card for you.
And our field trip is 10 to 2. What period of time can we do that so we can have different groups come here?
This is the equipment we use. We have this scale here, we have a board, and then we have another piece of wood that we landed on here. So this lab is just so students could understand the concept of center of mass. So it's theoretical point on the body where all the mass is evenly distributed around. So we use this to show them how it works. So they come in and everyone gets a weight on the scale, and they keep that in their lab notebooks. We know how much the board is weighed, so I usually show them the free body diagram, which I'll just show y'all quickly. I'll usually draw the free body diagram. So I have the scale, I have the point at the end, I have the board, and the person's already on there. And I draw the forces, so I just have 2 reaction forces, have the weight of the subject and the weight of the board. All I do is I write the equation of motion. Look at they're kind of learning about moments here. So I'm introducing what a moment is. I'm saying a moment is just a force times a perpendicular distance. And then we look at this picture and we just do that over and over. We'll say the force of the scale, we're taking the moment about this point. So I'll be like, we're going to take the moment about A. We look at each force and we multiply it by its perpendicular distance. And then they just solve for where the center of mass is for the person. So each student will get up on the board and then we'll measure what this F scale is. And then they'll plug that into here because they know the weight of the board. They'll write down what the F scale was. They know the length of the board and they know their weight. And then they'll solve for where their center of mass is. And then they do it with their hands by their side, and they also do one with their hands over their body because they're moving mass further up here, so the center of mass is going to move this way. So we're just kind of showing them, kind of like understanding how the distribution of mass is going to change that point. So that's kind of like the idea here. They're just learning about moments, they're learning about static equilibrium, and center of mass. And so this is kind of the equipment that we use to do that lab. Do you want to ask questions about that one now, or do I want to talk about the arm model?
You said this will actually be their weight, and then we'll figure out the mass from that?
Yes. This will give them their mass and their weight.
Okay.
So then, that's another thing. Like usually we'll like explain like to get a force, because they'll measure their mass in kilograms, and they'll need to multiply by gravity to get their weight. And then that kind of comes into play in the other ones too, like weight of the board. You have to be sure that's in Newton, and then the scale. They'll get this in kilograms, and then they'll multiply by gravity. I'm sorry. So when we teach them about moments, there has to be a direction. So there's this convention that says, if the moment, so I'm taking the moment about A, and I'm looking at this force of the scale, it's acting like it's pointed around the point, right? So it's going in this direction, which is counterclockwise, so that's positive. But it's just a convention that we tell them to use. So we're saying, if the moment goes counterclockwise, it's positive, and this is the hand. So kind of usually it's very easy to use, so you could just loosen it and then you could move the arm to whatever angle you want. There's a scale on the back of here that lets you change the angle. So I'll just start it off just here so I can show. Okay, this is kind of stimulating a muscle. So the muscle is like attaching here on the arm and pulling in this direction. So the main things that we change here is we'll let them change the attachment of the muscle. So you could change the attachment of the muscle. You could also change the weight that you put in the hand, and you could change the angle that the arm is at. So there's 3 things you could change with the model. So loosen it, and then I could change the angle that the hand is at. So this one is kind of similar to the other one. We usually draw a free body diagram, and again we're just teaching them to do moments as well and static equilibrium. So I usually draw this free body diagram. I have shoulder, elbow, hand, and same thing again. I take the moment about the elbow, and then I'll say, okay, the muscle force is acting here. I multiply it by its perpendicular distance minus the weight that's acting here times its perpendicular distance, equal to 0. And then we just get this equation. And then this lab is all about relationships. Like, they don't do any calculations. I just want them to understand what happens to the muscle force as I change the attachment of the muscle, as I add weight to the hand, and as I change the angle of the arm. So, do you have any questions about that one? It's pretty... You want to look at the model, or...?
Yeah, I have a question. So, the relationship between the angle and the force, is that linear or is it sinusoidal?
There's a cosine in there. So, yeah, because
So, if you're looking at geometry in your class, this might be really interesting.
Because that's the one they usually ask about. They'll look at this increasing, and then it's because in here you have this RW, which is this, and it's changing. It's like L cosine theta. So as this is increasing, it's like a function of a cosine, so it's not linear, but it does make this decrease. I don't know if that helps. But yeah, it's based on this, which has a cosine theta.
What happens when you change the point of attachment?
It changes, if I move out to like the distal one, it increases the RM, and then the muscle force would decrease. Because
Strong right here. If my muscle went outside of my body and hooked on like that externally, I'd be really strong.
Yeah, if you had a bigger moment arm, yeah, you would have less. You would need less force. Did you? Yes. If this increases, then this could get smaller and still balance this out.